How's it going, everyone? I hope you had a nice weekend. It's Sunday night, and I wanted to make sure that I got these solutions to the practice exam problems up for you before the beginning of the week. So, the first thing I'll say about this first problem is I really like this problem because it emphasizes a key point of computing the moment of a force about a point. So I'm going to take that for what you want and know that just like last time, I'll have a preference to at least include a decent portion of problems on the actual exam that are either from the practice exam or from the homework. So in this problem, we have a hatch door and we have a strut that's exerting a force on the hatch door to kind of, let me put my hand up here, lift it up. And the key thing that you need to realize when you look at this problem is that point A isn't directly below B. They don't lie at a common x value in an xy plane. This force from A to B is kind of angled up at an angle. So we know the diameter of the door, we know the magnitude of the force, and what we want to do is find the moment of the force about point O. So the key point here is to compute the moment of a force about a point. We're always taking a cross product of a position vector and the force. But the question is, what does that position vector have to be? And for all of the different moments that we spoke of in the chapter, and there were quite a few, there was always some ambiguity in terms of what position vector you could choose. And it's the same thing for computing the moment of a force about a point. You can choose any position vector from the point of interest, in this case O, right? So we're computing about point O to the line of action of the force. So we know, and I'll kind of go over here, that F has a magnitude of 450 newtons, and that the line of action of F is along an axis defined from the line segment from point A to point B. And the key thing is, again, this would be the last time I repeat it, I swear. The hardest part of these questions is in being able to read out the geometry from the figures that you're given. And what I want to make sure that everyone sees is that this displacement from A to B isn't purely along the z-axis. You actually have to go back into the yz plane a little bit as well. So the first step that you need to do here is kind of define the coordinates of A and B. And the reason you need to do this is going to be essential in order to write F in rectangular form, because remember, the way that we're going to write F in rectangular form is to scale its magnitude by a unit vector along its line of action. And the 2 points that we're given are A and B. So if we can write a position vector from A to B and scale by the magnitude of that position vector, we'll be able to write F in rectangular form. And in addition, these coordinates will be necessary for the position vector. So I'll just say that we need these for both the R and the F, regardless of what R we choose to use. We're going to be able, in this case, to use ROA, R, or ROB. So let's start with the easier of the two, which is point B. I hope you can see by looking at this diagram, and if you can't see it from my printout, go to the actual problem in my lab where it's a higher resolution image and you can zoom in and it's in color. But point B actually lies in the YZ plane. If you notice, its geometry is defined by a counterclockwise rotation in the YZ plane by 30 degrees from Y towards Z. So I can actually just draw in 2 dimensions in the YZ plane. And I know that point B lives out in this plane. It's elevated 30 degrees in the counterclockwise direction from positive Y to positive Z. And I know that since I know the diameter of this hatch door is 1 millimeter, I know that the distance from the origin to point B is 1 millimeter as well. So what that means is that I can get the YZ coordinates in this direction by just doing our traditional right triangular decomposition. I can say that the coordinate of Y is the hypotenuse, which is 1 millimeter, times the cosine of 30 degrees. And the coordinate of Z is 1 millimeter times the sine of 30 degrees. And in normal times, these are things that I would just read off. But in addition to being really late on a Sunday, it's like 1,000,000 degrees in this room right now. So if you've noticed any sweat on me, that is really sweat. It is so hot in here right now. This is 0.866, and this is obviously rounded. So we'll store these values. And Z is 0.500. So if you're working in either a programmable, easy for me to say, environment in your calculator, I think it's just easier to put these values in here. Or if you're taking a test and you have like a scripting language like Python or MATLAB open, that is great. So I have my values of B. Let me go back to my coordinate axis. You see, this is real sweat. Wipe it off here. So we'll now do A, which is a little bit more confusing. The key point for A is A, of course, is going to lie in the XY plane. Positive X, positive Y. But if you notice the geometry that we're given from A is related to a point that's 0.5 meters out along the Y-axis. So I'll show you what I mean by that in a minute. Let me go up here. So this angle, 30 degrees, is defined as a angular displacement from the y-axis towards the x-axis by 30 degrees, but that is measured from a line segment that comes out 0.5 meters along the y-axis. So we'll see why that'll be relevant in a minute. So here's our point. So that's 30 degrees. So I can do a decomposition here. I know that this is the radius of the hatch door, which is 0.5 meters. And I can find this point. The x-coordinate is going to be particularly simple, right? The x-coordinate is just going to be related opposite of that 30-degree angle. So it is just going to be 0.5 times the sine of 30 degrees. So everyone see why I use 0.5. That is the radius of this hatch door, which is related to the geometry that we were given. However, when we compute the y-coordinate here, right, the y-coordinate is going to be this base of the right triangle here, which is going to be 0.5 times the cosine of 30 degrees. But we're going to need to add on that additional 0.5 meters from the origin that we started based upon the information that we were given. So I'm going to say that A is equal to, and the x component is going to be 0.5 times sine of 30. The y component is going to be 0.5 plus 0.5 times cos 30. And it has no z component because it's purely in the xy plane. And what I find is that x is 0.250 and y is 0.9330. Okay. So we have, believe it or not, all the information that we need here. Because next, so we'll call this step 2. We'll write f in rectangular form. So remember, to write f in rectangular form, we just need to multiply that magnitude by a unit vector along the line of action. In this case, we can see from our original problem geometry that f is directed along a line from A to B. So I can say u, I can write it as RAB divided by mag RAB, where RAB is just going to be the x-coordinates of B minus the x-coordinates of A times I hat. Do the same thing for the y-coordinates and do the same thing for the z-coordinates. So the only real mistake you can make there is doing tip minus tail in the wrong direction. So I'm just going to take, since I have this in a scripting environment, and write B minus A, and I'll find that RAB is the vector, and I'll go back to my .chem in a minute, minus 0.2.5 in x, minus 0.067 in y, and 0.5 in z. And it's good if you want to kind of look and do a little bit of a sanity check and make sure that at least your signs are right. If you notice to go from A to B, since you're going, let me zoom out a little bit. Since you're going into the YZ plane, that displacement will be in negative x. Okay. In addition, it may not look like it, but it has a little bit of a negative y component, as we see indicated in the sign and small magnitude of the y component of this position vector. So just to make sure this is RAB, we still need to find the unit vector. And of course, to go from A to B, you go in the positive z direction. So going back to our dot can now, we can say that UAB is just RAB divided by that magnitude. So there is, if you're, I don't know how many of you would be using MATLAB here, but just in case you are, there is a command to actually compute the magnitude of the vector. And of course, I'm not, is it norm? Sorry, you're seeing this in real time. I think that's it. But let's actually verify what it is. And the way that we will do that, since we have the individual components stored in the vector RAB, I'll take the first component of that, I'll square it, and I'm just going to copy and paste to make my calculation easier. And I want to emphasize, you don't have to use a scripting language, but I know that the vast majority of you want to transfer onto a 4-year degree. And being able to do this in software, particularly when you have that ability at your disposal, is going to be quite powerful. So we see our result is the same as when we just took the norm of that vector. So that is the correct function there. But if I wanted to actually compute what the unit vector was, I can divide the position vector RAB by its norm, and I will get this solution here, minus 0.444, minus 0.119, and 0.8881. So going back to my dockin, just to show you what I have there. And that, of course, would be unitless because this was in units of meters, this was in units of meters, and those units cancel. Therefore, I can say that the vector f is just going to be mag f times scaling that unit vector. So I'm just going to take that answer that I have in MATLAB here, and I'm going to multiply by the magnitude of f, which is 450 newtons. Sorry. So parentheses to make it clear there. So hopefully, whatever calculation approach you are doing, you were able to get this expression for the force vector F in newtons. And we'll go back to the dockin just so everyone can see that. So however you did it, the approach here is you're given the magnitude of a force and you're given enough information to write an expression for its unit vector. We know that it's directed from A to B. We can get the coordinates of A, the coordinates of B. We can write a position vector between the two by subtracting the coordinates on a per coordinate basis and scaling by the I hat, j hat, and k hat vectors. Once we have that unit vector, we take the magnitude and we scale it, and we get an expression for the force. And again, we need this expression for the force because ultimately what we want to do is take a cross product, and we know in 3 dimensions that's easiest to do if we have an expression for the vectors in rectangular form. So the question is, finish this off, compute the required R vector. And the key point I want to emphasize here is you can use 2 different ones here. The first that you can use, so remember, why can you use 2 different ones? The definition for the moment of a force about a point is the cross product of a position vector and a force, where that position vector, it has to start at the point of interest, but it can go anywhere along the line of action of that force. So since we know 2 points along the line of action, we can either compute the position vector from O to A or from O to B. And in either case, because the kind of tail of the position vector is the origin, these are going to be very, very easy position vectors to compute. In fact, we already have them stored in our software. So this is just going to be just to show you what I mean by that. This is AX minus 0 I hat. And again, this is because this vector originates at the origin. Plus AY minus 0 J hat plus AZ minus 0 K hat. And we know that for point A, this is going to be the X component, 0.250. So this is just coming back from this line that we did above. Y component, 0.9330, and Z component, 0, and that is in units of meters. Therefore, using this approach, we can find the moment of that force about 0.0 by taking the determinant of the matrix that we get, 3 by 3 matrix, putting the rectangular unit vectors in the first row. This is going to be our ROA, our position vector from the point of interest to the line of action of the force. And then we need our expression of our force that we just have here. And trying to show, like, in case you're actually copying my work and typing it into a calculator, enough precision that you won't run into any rounding errors. But the preferred way to do this would be to keep those values stored as variables in whatever computing environment you're using. Remember that to compute the determinant of this matrix, you just do a cofactor expansion where you start along the first row, you cover up that first row, you cover up the first column, the resulting 2 by 2 matrix that you get. So if you cover that up and cover that up, this 2 by 2 matrix here, its determinant will give you the I hat component. Remember, when you go to j hat, you do a minus, and if this were a bigger matrix and you were doing an expansion, it would continue to alternate plus, minus, but we only have 3 here, so that's okay. This is going to be 0.250, 0, minus 199.816, and 399.63, plus k hat. Cover up the first row and the third column, 0.250, 0.9330, minus 199.816, and minus 53.54. Remember, you're going to take the cross products this way minus this way, so that's going to be I hat. And it's going to be 399.63 times 0.9930 minus 0. Here, for the j hat value, it's going to be minus j hat. In that downward diagonal, we'll have 0.250 minus, times 399.63 minus the upward diagonal. We'll have a factor of 0 in there, so that will be 0 as well. And for the k hat component, we got terms on both diagonals, so we have to be careful here. 0.250 times minus 53.54 minus, along this direction, there's going to be another minus, so it'll be a positive, 199.816 times 0.9330. So I'm actually not going to show you because I'm going to use a calculator for that, as I hope you are doing too. So this is, if you think about it, it is the vector that we've called in our software A crossed with F. So let's make sure we got F saved in here. I don't think I did do that. Where would I have had that at? I got this. Let me, this is the unit vector. Yeah, here we go. Let's say F equals answer. And then I want to cross vector. If you look, I have vector A stored in my software, so I can just cross A and F. And I will get 372 to 3 sig figs. That would just be 373, sorry, for my X component. My Y component will be minus 99.9, and my Z component will be 173 flat. And that is going to be in units of whatever the units of the force were, newtons, times whatever the units of the position vector were, meters. So that is going to be one expression for the moment of that force about O. So I will circle that. And what I will show you here, if you look at that result that we have, if we were to compute the cross product of the position vector from O to B and F, we would get the same result. So notice that these are the same in these cases. So I'm going to be scanning the solutions. So I will just say, can verify that this is equal to ROB cross F. So hopefully that was helpful for you, I guess, in terms of the more strategic things that would generalize across this problem. Just know that when you compute the moment of a force about a point, you have to find a position vector from that point to the line of action to the force and take the cross product with the force itself. This kind of reviewed the concept of how to compute the unit vector along a specified position vector. And in addition, you got a little bit of review of how to, given the magnitude of a force, how to write it in rectangular form if you know that unit position vector, and just a review of how to take a cross product as well. The main kind of operational thing that made this problem hard is you had to be able to read out the relevant geometrical information from the problem statement. And kind of to account for that, I would be very tempted to use this problem again in an exam.